welcome back, guys. Let's go ahead and continue talking about the sun. And I promise you, Girl Scouts honor, no more equations this time. But they were a necessary part of life to talk about what's going on in powering the sun. So, start out with the sun here. So last time we went ahead and talked about the reactions then that are fueling the sun. And so today I want to go ahead and talk a little bit more about the core of the sun, and then I have some really cool pictures to go ahead and show you toward the end that will kind of get us into looking at characteristics of stars and looking at the light that we use to determine what those characteristics are. So, nice picture of the sun out there, guys. Now, if we talk about our sun, we know currently our sun, as with most stars that are kind of doing their normal thing, are in what is called hydrostatic equilibrium. Now, I want you to think that there are two forces that are going to really occupy a star's lifetime. One of them is going to be gravity, which you're quite familiar with, and gravity is always going to tend to compress that star, compress our sun. Just like if I had you step off of a table, guys, you're going to go straight down. Okay, so you're going to tend to fall inward, and that's exactly what happens with gravity on a star. And gravity is certainly the most important factor that occurs or that influences a star's lifetime. Well, that gravity, that weight per unit area looking inward, is opposed by something called the hydrostatic pressure outside. So you have the pressure from the energy that is being produced inside that core. That energy is being given off and it is flowing through the star, and it produces this outward pressure. And so most of the time a star is in, like I said, that hydrostatic equilibrium, which means that these two forces, one trying to pull it in, one trying to expand it outward, are definitely in equilibrium. So if I go back and I look at then those parts of that sun, so where are we getting that pressure outward? Well, the core of the sun is about 25% of the solar radii. And it's a place where you have that nuclear fusion occurring through that proton-proton chain. And like I said, guys, that's what's been powering the sun for the last 5 billion years. That's what's going to power it for the next 5 billion years. Now, that energy that's produced by that proton-proton chain, which remember is continually being recycled and going through and producing more hydrogen. So ultimately, when we get to the end of that about 10 billion years, we will have slowed that reaction some because you still have so much hydrogen that has been used and you've built up that helium. Most of the time, that energy that is given off takes a while to actually go ahead and reach the outer layers of the sun, that sun's photosphere. And once it does, it's going to escape into space either as sunlight, which is kind of what we see, although keep in mind, we're looking at that sunlight in the whole electromagnetic spectrum range, or the kinetic energy of the solar winds. And we saw the solar winds when we were talking about comets that always had the tail of, at least the ion tail of the comet, pointing directly away from the sun because of those solar winds that were pushing it away. Seen this picture before. You know, looking at that core, looking at those radiative zones, looking at those convection zones, and then looking at that photosphere, that chromosphere, and the corona. So let's talk about that radiation zone or that radiative zone. It goes from the core up to about 70% of the solar radii. Now, remember, guys, the pressures inside that core are incredibly hot, incredibly great. Very high temperatures, very high pressures. And so that energy, when it comes out, is hot enough and dense enough to go ahead and transfer the energy outward through thermal radiation. So that makes basically heat. So there's heat that is radiating outward. And remember I said that as you move out from the core, for the most part, the temperature and the density are going to decrease. And that's certainly true here. So that temperature is going to decrease as my altitude increases, and it goes from about 7 million Kelvin to about 2 million Kelvin, and the terms of our densities go from about 20,000 kilograms per meter cubed to about 200 kilograms per meter cubed. So again, we're just talking about what's going on within that radiation zone. Now, between the radiation zone and the convection zone, you have a really thin layer that's called a tachyocline. Now we look at that, and because you have this really thin layer, a lot of times you're going to get a really large shear between those two layers because you're going from a radiation zone to these big convection currents. And so we have shearing there, and that shearing causes the horizontal layers of the sun to go ahead and slide past each other. Now remember, these are gases. You're going to get a lot of friction built up. These gases have lost their electrons, so they're in the form of ions and particles. And we think that that shearing effect between those two zones is helping to produce the sun's extremely large magnetic field. So the convection zone, we're going to have these big convection currents set up. So we actually are moving mass from down below all the way up to the surface of the sun, or up to that photosphere. Remember, guys, that they get hot, things get less dense, therefore they rise, they get to the top, they cool off, and they sink. But it's, again, this huge amount of mass that has been brought up, cooled, and then sinks. And notice that as that mass moves upward, obviously it's going to cool to the temperatures that we see on the surface of the sun. And once that has lost enough energy, then that's going to fall again. You know, and we see plenty of convection currents set up here on the Earth, so we know that the same process that we see here on the Earth is basically doing the same thing on the sun. And so this is just kind of showing you, you've got a heating source, which is what's going on with the core, then you get that material that's being radiated out, that energy that's going through the radiation zone, and so that then goes ahead and heats the mass goes ahead and rises. You can see that it gets up from the top, it cools off, it sinks, and it goes through that whole cycle again. Now we see the tops of those convection columns as what are called solar granules on the surface. Remember, guys, I said that I wanted you to go watch water boil? I know, it's not a really exciting process, but I really want you to go watch water boil because that gives you a feel for what the surface of the sun looks like. These little granulars that are on the top of the sun are about 700 to about 1,000 kilometers wide. That's about 400 to about 625 miles, kind of going from the metric system to the English system. And they seem to be really bright areas surrounded by really narrow, dark regions. And so they come up and then they go ahead and sink. And they last for 5 to 10 minutes. And I've got a YouTube video down here that I want to go ahead and play, but part of this I'm just going to kind of skip over. But I do want you to see these granulars. So we're obviously seeing the surface of the sun. If you look very closely, guys, you're going to start seeing it boiling and seeing motion in there. Now, they've got this slowed down, so you can kind of see what the clock is doing on the side there. Later on, they're going to show you a little bit closer where you really can see that surface as it's moving and boiling. And it really does look like, as it pops up right here, it really looks like that boiling, seething surface there. You can almost see that heat that's being given off. And so you notice the tops of those granulars, and then you are surrounded by that very narrow, dark band. So it comes up, and then it goes ahead and sinks down. And then you just keep repeating that cycle over and over and over again. Just another picture. This happens to be a still picture of those granulars. Now, there are other things that you see on the surface, and those are going to be things like sunspots and Plages and Prominences and all kinds of other things that we see there that we'll have to talk about. But the other thing on this one, notice that we're coming up. So we're starting out down at that level of that dark spot, which happens to be a sunspot, and you come up, and now we're starting over again. Just to give you an idea of size, guys, you see the Earth over there in the lower right. I mean, that's a really large area on the sun, guys. You know, and so you're looking also at those kind of areas that almost look like they're spikes, you know, or strings. Well, we're looking at the magnetic field right there. Now, you were just looking at that. You were looking at that photosphere, and the sun's atmosphere, which basically is that corona and that chromosphere, is transparent until we get down to the photosphere. And like I said, guys, I know I refer to the surface of the sun, but you know, it's not a solid surface. It's just where it's no longer transparent and it's very opaque and we can't see anything below. It tends to be visible because of the decreasing amount of those hydrogen ions. And with that visible light, we also see it due to the production of hydrogen ions. And we'll look at that a little bit more with an activity that I am going to have us do. Thickness ranges from about 10, to about 100 of kilometers thick. And notice that I have the next statement in blue. If you go back and you look at the original periodic table, and you look at, as they were trying to put the elements into the periodic table, it was recognized that column 8 is something called the noble gases. Those noble gases are noble because they don't react with anything. Well, we felt like there was an element there that we had never been able to find but should exist. And so we found it on the sun. It's called helium, hence the name helium for helo. Helium is a very, very, very light element. And so the problem was if it was produced here on the Earth, which we know it is now, it gets out to the atmosphere, the sun heats it up, it gets very energetic, and it leaves. Well, we found helium when we first, by looking at that spectrum on the sun, it fit all the right characteristics, so we knew we had found one of the lightest of the noble gases. Above the photosphere, then, is the atmosphere of the sun. That's composed, like I said, the chromosphere, the corona, and then the heliosphere. The atmosphere of the sun, as I've said before, is much hotter than the surface of the sun. So we're going from this 58K to these millions of degrees in a very short period of time. So let's talk about the chromosphere. Chroma means color, and so we're going to find out that chromosphere is actually a very red color due to the really strong red line in the hydrogen spectrum. So you have this transparent gas layer, which is about 1,500 miles thick, and that's going to extend then beyond that photosphere. So the photosphere, then we go up a little bit, and we're going to see the chromosphere. Unfortunately, a lot of times the only time you can see it is during an eclipse, and it's going to show up as a really red streak around the moon, or when you look at that moon that's right in front of the sun, you're going to see that really bright red line. And I've got some pictures of that here in just a minute. But again, that's because of that really strong red line in the hydrogen spectrum. We see a spectrum that shows emission lines, which makes sense because that energy then has been absorbed out by the gases. The gases then will spontaneously give that energy off, and so you're going to see those very bright emission lines. We also, because you are also going through the outer envelope, remember we have those gases that are going to absorb that energy out, so we see both emission lines and absorption lines. Now guys, you're looking at the moon in front of the sun, and so you're seeing that very, very, very distinct red color, and that's what I'm talking about when I'm saying you're seeing the chromosphere. You see the sun right there before you get into that total eclipse, or you're in a total eclipse, and you see that red band. It's kind of neat because like down on the lower right, you're seeing some flares going off, prominences, things like that. Just another picture of that very red part of the chromosphere. Now this, on the other hand, we're kind of back in that same area, but you can also see the surface, that photosphere, and then you see those very red, distinct lines. Again, we're looking at the magnetic field there. Now we know that the temperature increases with increased elevation at this point. And that's, if you look at our atmosphere, as you go up, it gets very cool and then it starts to increase. And the top part of our atmosphere is very hot, but it is not very dense at all. Circulation patterns are very complex, and they contain many of those jet light spikes, and we call those things spiculas. They can go ahead and last only about 10 minutes. Look at the speeds that they are moving upwards at about 675,000 miles an hour. Think about that solar wind. That wind is actually going to be moving a little bit faster. It comes streaming out of the sun. Even as big as the sun is and as massive as the sun is, it can't hold those particles in that are moving those kinds of velocities. Reaches heights of about 30,000 or 3,000 to about 12,000 miles into then the corona. Those are just those spiculas, and again, definitely think they're related to magnetic fields, things like that. Just got several pictures of them. Now this one, notice, is not the same. This is a nice green color. Again, you're looking at different elements that are in the sun. This is obviously an artificial color to bring out the different chemicals. And I've got an activity on Blackboard that I'm going to have you take a look at that kind of shows different views of the sun, where we're going to look at the types of chemicals that they're talking about there, and also the types of energy, because we'll see these kinds of things in, X-rays, ultraviolet, radio waves. How does the sun change during each one of those appearances within a particular part of the electromagnetic spectrum? Just looking at those very tops of the layers of the sun as you're looking down then into the photosphere. I personally think it looks something like this really abstract art painting. It really is the tops of the sun, guys. And then we're looking at this transition region that goes from the chromosphere to the corona. Very, very thin. I mean, we're only talking about 12 miles or so. And look at what those temperatures do. They go from about 10,000 Kelvin to about 1,000,000 Kelvin within 12 miles. So now we get into the corona, which is that outermost layer. Think of that as the sun's atmosphere, and you only see it during an eclipse. Very, very low density, but it's very hot. And we know those spectrum lines show very strongly ionized iron and nickel and argon, calcium, excuse me, things like that. And so that's another reason I kind of want to give you a feel for what the sun looks like with the artificial colors showing you, what's iron, what does it look like in nickel, argon, things like that. This is just a picture of the corona. Notice the sun is in eclipse. And you'll see that then change because it is moving. It's dynamic. It's certainly not static. It's continually in motion. This is just another picture showing you in grays the maximum temperatures you're going to get closest to the sun, and then it's going to decrease in temperature as I move out, as well as it shows you that dynamic motion within the atmosphere. Here you're seeing a little bit of the chromosphere, and then you're seeing the corona. Now, this is a solar spectrum. I kind of showed you one earlier. This is where Cecilia Payne, as well as other people, are looking at the abundance of the chemicals within the outer envelope of our sun. And notice, guys, that you can see absorption lines, and there are patterns of those absorption lines that correspond to, whether it's, argon or krypton or carbon dioxide or hydrogen, and so you have to very carefully match the position of those spectrum lines with known lines so that you can tell what elements we're talking about. Like I said, the corona is very, very bright in the X-ray part of the spectrum simply because of the high temperatures. We think those high temperatures are probably doing to the sun's really strong magnetic field. And notice you get those looping effects. If you remember what it looks like when you played with magnets when you were way back in the 5th or 6th grade, going from one pole to the other. And so you get lots of interference in there, and so you get force fields set up. We are not going to go into a lot of that detail, because you're not really studying the sun. I just want to give you a feel for what the sun is like. But if you are someone that really looks at the sun, trust me, you will map those things out and try and figure out exactly what's going on. And then we've got the solar winds, which we've already kind of alluded to earlier. These protons and electrons, as well as these charged particles that, are just coming out of the sun, and they're coming out at speeds approaching 900,000 miles an hour. That's almost 1,000,000 miles an hour, guys. And, at that point, as I said earlier, the sun simply can't hold them. So it heads out. And if we happen to be in the way, us being the Earth, then we're going to go ahead and probably have lots of really cool northern and southern lights. Like I said, they're not visible in visible light, but they certainly are visible in X-rays. And they account for approximately, notice that, guys, 10 million tons of material that leave the sun every year. Luckily, guys, we know that the sun is really massive, so we don't have to worry about the fact that we're losing 10 million tons of material. It's still going to last a really long time. We also think that probably gases between the magnetic fields are also free to leave. So they've been accelerated by that interference of those magnetic fields. As the fields get jostled about and moved about, attracted one to the other. And so we think that's happening as well. And the next series of slides they've got just kind of show the magnetic field of the sun and show the corona, as well as some of the interactions when you're looking at the sun sideways from what's going on that surface. You see some coronal holes right there. And then you also have, remember we talked about what was going on between those magnetic fields, and that's when they're talking about being ejected from those activity centers. And so there's still a lot going on within the sun that we're not quite sure about, but we're beginning to get a good feel for what's happening. Just a flare on the sun moving outward. You see that big, massive coronal hole in black coming through there. Again, if I hadn't told you that was a sun, I think it looks really cool, like an abstract painting. X-ray picture of the sun with those incredible coronal holes. You can almost see those little spiculas coming out from the sides of the sun. Just another one. This one, the sun has been artificially eclipsed, and so you can see the atmosphere of the corona here. And remember I said we do have the SOHO telescope that's in orbit around the sun, and so this is providing a huge amount of information that we can use to study what's going on within the sun. And right down there at the lower left, you can hardly see it, is a comet going around the sun. Just another big, huge prominence. Guys, remember, we can fit 110 Earths across the sun, so knowing that, realize how large that is, that prominence that's coming up off the sun. And you can almost see that curving, so we're going from one pole to another pole. Now, luckily, we're protected on the Earth by the Van Allen belt, which is really good, guys, because if we didn't have that, we would really be in trouble. So when the solar winds go ahead and reach our magnetic field within, the Van Allen belts, then we get that energy of those particles that are directed toward the north and south poles, and we get the auroras. I've never been lucky enough to see the northern lights to this extent. I have seen them here down in Missouri, in Springfield, and usually by the time I see them here, they're really red. They're not those really phenomenal, beautiful colors. Notice that you can see the stars through the northern lights. And so we'll have the northern lights and the southern lights. And they're just interference from the solar winds on the sun that run into then our Van Allen belts, our magnetic field. I can imagine what that looks like when it's in motion. And so you get these incredible ribbons of light moving across the sky. Definitely, guys, a reason to either, one, take a trip way up north or to head way down south. Certainly one of the things I want to do on my bucket list. Things I want to do before I go away. Then we have sunspots. And sunspots are darker, cooler regions on the sun's surface. And every once in a while, guys, on the news, the weathermen will go ahead and say, hey, there was a really, really, really big sunspot on the sun. And, some people have looked at the sun. It's down on the horizon. It's looking through lots of atmosphere, and they see blotches on the sun. And that's what you're really seeing are sunspots. Like I said, so they can at times be seen with the naked eye, which means, guys, they're really big. They last from a few hours to a few months. Luckily, we can go ahead and trace what they're doing, and so that's how we got a good feel for how long it takes the sun to go ahead and rotate, is by watching sunspots move across its surface. They generally come in pairs. You generally have individual spots that show a really dark area, which we call the umbra, and then a lighter outer area, which we call the penumbra. Guys, remember we saw that on eclipses as well. Like I said, they frequently occur in really prominent pairs surrounded by smaller spots. The two prominent spots have opposite magnetic poles, either North Pole or a South Pole. And then the leading pole are the same in one hemisphere and opposite in the other. So we definitely know there's something called a sunspot cycle. And we know that then the next time they come around in that cycle, they tend to reverse. We also know they're driven by the sun's magnetic field. And there are two cycles. One of them is a maximum to minimum cycle, and the other one is a 22-year cycle where we reverse our polarity. That 11-year cycle means, and it's not an exact 11-year cycle. Please realize that, guys. It's an approximate. And in some years, we have maximums that never have a really bright or large sunspots. And then we have minimums that shouldn't have very many spots, and we do have lots of spots. Just kind of depends. But in general, approximately every 11 years, you go from a maximum sunspots to a maximum sunspot. Okay? And then on that off 11 years, then you get down to a minimum. And then, like I said, the 22-year cycle means that, for an 11-year cycle, we have a south pole leading. And then the next cycle that comes along, the north pole is leading. And then you take that 22-year cycle and it comes back, and now we start with the same one that we did have the cycle before. The Zeeman effect is just one way to go ahead and measure the magnetic field strength. And when you use that, and we're not going to worry about exactly what that is. If you take some chemistry, you're probably already familiar with it. But if you take measurements using that effect, then we find that that magnetic field is extremely strong. And then we have regions that are very active on the sun. And these include sunspots, Plages, prominences, flares, things like that. Now, those sunspots we've kind of already talked about, guys, and I said that they are visible with the naked eye. Please do not look up at the sun and look for them unless you have been told that it's safe and you're down on the horizon and you have lots and lots and lots and lots of clouds that you're looking through and you're seeing that beautiful kind of really reddish orange sun, and then it's somewhat safe, but don't stare at it. Okay? Better way is if you have a pair of some kind of goggles that cut out a lot of the UV light, things like that. If you've got an eclipse or something like that, then it's appropriate to use that. But it's never a good idea, guys, to go ahead and look at the sun and stare at it. You'll have spots before your eyes, and you can burn the back of the retina of your eye. So besides sunspots, we have Plages, we have prominences, we have flares, all these wonderful things that occur 93 million miles away from us and have a tendency to influence what's going on here on the Earth. They all have similar longitudes and latitudes, but they're going to go ahead and occur at different heights within the atmosphere. So they're kind of located, same general area, but they're sitting on top of each other. And as I said before, they are simply always associated with a very strong magnetic field. So these Plages are clouds of calcium and hydrogen and other elements that are going to be around the sunspots. And they're going to show up as really bright areas. And they have a higher temperature and density than the sunspots. So they're going to show up as really bright areas around these dark spots. The dark spots are the sunspots. And then these bright areas down there are in the Plages. And they show up very easily if you look at some pictures, of which I'm going to have some URLs that I certainly want you to look at on there. Show up as, when I look at the spectrums, these predominantly calcium and hydrogen, so that you can use that to kind of figure out what's going on. And these prominences are going to then occur a little bit higher. They, like I said, originate higher in the atmosphere. They're also usually found around the sunspots. So we think that these are different views of what's occurring in the different layers as we move upward from that sunspot. If I look at them from the side, they appear as red, flame-like prominences or protrusions that are going to rise above the sun, and they're reaching a lot of times high into the corona. And we know that they can last for many hours or many days. And what's really cool, we can go ahead and photograph them right as they're taking off and forming. It's these huge things that just come up, welling up from the surface of the sun. And then we have flares, which are, again, higher in the atmosphere. Very rapid eruptions on the surface. They just spew material out. They last from about 5 to 10 minutes. If we're in their way, then we're going to have that material that comes out, a little bit later. They can release as much energy as 1 million hydrogen bombs. And they are certainly most active during the sunspot maximums. So again, all this seems to be interrelated. Okay, now why am I showing you a picture of a really, really, really badly destroyed satellite? Well, that's because, remember I said that most of what we see from the stars and from the sun and from the planets do come from the electromagnetic spectrum. Now, in this case, this was a satellite that was in orbit around the sun. It was in orbit around the sun for several years, and it was designed to collect particles that were given off by the sun during flares and during prominences and during solar winds, things like that. And then the idea was, go ahead, let it go around the sun for a while, bring it back. We can then go ahead and pull those detectors out, and we can physically have particles of the sun then in a laboratory to go ahead and work with. Well, it didn't exactly come down to Earth the way that we expected. We had some issues, and so it hit the Earth much, much, much faster than what it was supposed to, and unfortunately, those are the results. Now, luckily, we were able to salvage, so scientists were able to salvage some of the detectors, but a lot of them were destroyed. But there are at least some that were salvageable, and they used to go ahead and work with in the laboratory. So that's why that thing is there, even though it's kind of smashed. That was one of our probes that we had around the sun that physically brought back particles of the sun to us to look at. Now, this, on the other hand, is SOHO telescope that's in orbit around the sun, and that's a comet that's heading into the sun, and it was amazing how many comets we actually found once we were up there looking that we never see that get, pulled into the sun by the sun's gravity. Lots of comets out there that never get close enough, never get big enough, but yet, they are certainly getting pulled into the sun. So the question is, are they small enough that they don't have any impact at all when they hit the sun? Or exactly what happens? The next series of pictures, guys, I've got are just pictures of the sun and hitting up into the corona, just to kind of show you some different versions of it. Here you're seeing those sunspots as well as those Plages, and you can see they show up very easily as those brighter areas. In fact, on this picture, you have a really hard time actually seeing the sunspot. Okay? But there are sunspots there that are associated with those brighter areas. Sunspots are cooler, so they show up as darker areas on the surface. We also occasionally see these things just literally appearing to streak across the surface of the sun. And some of the URLs I'm going to have you look at, you're certainly going to see that. Just literally streaking across. I mean, it looks like the entire sun, through a very short period of time, just has this fault line that opens up, and you see down into it, and it's extremely hot. Looks pretty cool at the same time. Sunspot pairs, you can see one certainly in the middle of the sun. You also see one coming around on the left side. They pretty well stay, in those spots as they move around the sun, and then they will gradually fade. You can see that generally they compose of, two prominent spots and lots of little spots around it. That's a weird looking spot. So you have a nice sunspot that's kind of about halfway to the middle and a little bit over to the right, and then you have that other weird sunspot. Okay, is that really a sunspot, guys? And that answer would be no. This one, you happen to take a picture of the sun, and the space station was between us and the sun, and so you happen to take a picture of the space station as well. And so that's not orbiting the sun, that happens to be orbiting the Earth, and it just happened to be between the Earth and the sun, so I thought it looked kind of cool. Same thing here. Notice that you're seeing that nice space station making a transit across the sun, and it just happens to be between us and the sun, and so you're seeing it there. And then that little black spot is Mercury. Now, guys, obviously I have the orientation. Now I've got the sun where you're looking at spots that are above and below the equator. So imagine the orientation of this picture has the sun's equator right through the center, just basically dividing that sun in half. And so I have spots on either side. If you have a sunspot maximum, then you're going to get lots of those spots visible. More spots. You can see the rotation of the sunspots here. And so if I then go ahead and measure how long it took those spots to move across the surface of the sun, I get a feel for the rotation. Remember I said that the sun does not rotate as a solid body? So depending on where those sunspots are in relationship to the equator, then will give me a feel for how the equator is rotating compared to how the poles of the sun are rotating. Now, guys, this is the same spot, just taken, all the way as it's moving across then the surface of the sun, and you can see that the equator of the sun is right there in the middle, and so we have sunspots on the northern hemisphere and sunspots on the southern hemisphere. And then what you do is you very carefully go ahead and measure how long it takes for those spots to move. So that is a sunspot. So we're looking all the way down at the bottom, and then remember those prominences and flares and things like that just happen to occur around the sunspot because they're related to the sunspot, only higher in the atmosphere. Close-up pictures of sunspots, lots of little ones. Those are those flashes that tend to be associated with the sunspot. Like I said, it's opening up, especially if you catch one right as they're forming. You know, it looks like then that you are looking down into that sun. You know, it's almost like you're pulling away the surface and you're seeing this incredible energy that is down below. It's a better picture of a sunspot showing then the granulation. And you can almost, like looking at that, get a feel that that sunspot's a little bit deeper. Okay, and then I'm coming up and I'm seeing that granulation. Same kind of thing, just a different view. We're now looking more toward the top part of the atmosphere. And so you're getting those speculas forming. Again, all of this tends to be related back to that really strong magnetic field. The picture of a big prominence or flare coming off the sun. You can almost see a little bit to the upper left of that. Kind of looks like you have material that's streaming out from the sun. More toward the higher end of the spectrum, more energetic waves, but it gives you a different view of the sun. This is more toward the X-ray part. And then you can kind of see that material coming out. And like I said, they will come out. They got enough energy. The sun can't hold them, and they take off. Notice the approximate size of the Earth. Notice the size of that flare. Again, you don't realize quite how big that sun is until you look at a picture like this. And we're very, very, very tiny compared to the sun. You can certainly tell when you look at these, which ones of these pictures are a little bit older compared to where our newer technology has given us better images of the surface of the sun. This is one that was caught just as it was taking off. I mean, you can use your imagination to see that thing leaving the sun. And so this one is just kind of a repeating cycle. It has come out from the sun. It's got enough energy, the sun can't hold it, and it would just continue outward and onward. Or onward and outward, whichever way you care to look at it. Just a picture of the Chromosphere. Obviously, we're in an eclipse right now. I don't know why, but I really like this picture of the sun. I guess because it really looks incredibly large, and you see this incredible flare prominence coming off. Now that's another one that to me looks like an abstract painting, but in reality, what you're looking at is the top of those flares and those prominences. Prominences generally because they're going from one pole to the other, and you're looking now down at the tops of them, and so you can almost imagine that they're coming up and then they're curving back down and around. I still like it as an abstract painting, but it is real. You know, you're looking at those things coming up and going back down. And so think about those horseshoe magnets you used to play with as a child and what the magnetic field was doing between those two. Now, this is not a real picture. This is an artist's conception of what's going on with some of the magnetic fields and how those fields interact and how those fields get jostled about. And then the picture on the lower right is, though, a real picture, an actual photograph. And those bright areas, I think, are where those magnetic fields then are really shining through and where they're very energetic. Another abstract painting. that is really the tops of those prominences again. So imagine when you're looking back at this picture and you're looking at the tops of those big prominences that are coming and flowing from one to the other, and then you're sitting on top looking down on these big domes, and that's what you're getting there. Some of them are more energetic than others. Same thing, only you're looking at, again, a graphing of the equations that are dealing with describing then what you're seeing. But those big domes as you're flowing from one pole to the other, South Pole to a North Pole, or North Pole to a South Pole. That looks a little bit out of focus, doesn't it? Well, it's really not, well, it is out of focus, yes, guys, but I mean, it's supposed to be that way. It was so small when they took it, but what you are looking at is you're looking at a tornado on the surface of the sun. And so they've had to bring out that detail as much as they possibly can. And so you do see it pixelated quite a bit. But guys, you're seeing a tornado on the surface of the sun. Lots and lots and lots of stuff that we still don't know nor have a good feeling about what's going on with the sun. But there's lots of cool things that we're finding out all the time. Shock waves moving out from events on the surface. Same thing, you're looking at that side tornado coming through. So we do see these areas that are very active on the sun. We see movement. We see spiraling things. They're very small, which is why you see them more as a pixelated version as opposed to a very nice, very sharp image. But like I said, just think about what you're actually seeing. Very active areas. And remember, whatever happens there does have a tendency to influence us when we're 93 million miles away, sometimes more than others. We know that if we've got lots and lots and lots of sunspots going on, that has effect on what we're doing on the Earth. Look at that one. It's taken in X-rays. You almost can see the seething energy coming off of that thing. So let me end with that. Nice picture of the sun, very benevolent. We're looking at it through our atmosphere. But keep in mind, guys, that sucker's 93 million miles away. We wouldn't exist if it wasn't for that. And what happens on that surface, what happens inside that sun, eventually affects us, as well as every other planet in our solar system. So now what I want to do for the rest of the unit on stars is go ahead and compare those stars out there with what's going on with our sun. We know our sun is right now in the middle of its lifetime. We're going to look at what happens as it starts evolving. It's no longer converting hydrogen to helium inside that core. And we'll look at other stars out there that have gone through that same converting hydrogen into helium and is no longer doing that to see what happened to those.